Hello, welcome back to part 2 of our look at the respiratory system. And in this video, we're going to be more focused on, again, building that foundation of understanding about what is happening here and what is really regulating the process. So this is all about regulation of breathing. And then in our last 2 videos, we will get more into the physiology of it. So what is actually happening once we have an understanding of what's regulating this process. And so with that said, let's go ahead and jump into our look at part 2 of the respiratory system, which again is dealing with regulation. And I start with kind of an overview of, or not even an overview, but I guess maybe a reminder of, a review of what is happening as we are breathing in and what is happening as we are breathing out, or the more technical terms that we need to be mindful of is what is happening as we are conducting inspiration and what is happening when we are engaging in expiration. Inspiration is that process of breathing in, and then expiration is the process of exhaling. And this is mainly referring to external respiration. And so that is another key factor to keep in mind. That this here is referring to external respiration. And so, again, what does it take to conduct inspiration? Well, the diaphragm has to contract. All right. The external intercostals have to contract, and as they contract, they expand the rib cage. They pull on the ribs. And what does that do? Why is that important? Well, from the last video, we know that that is going to increase the volume within the thoracic cavity. We have an increase in volume, and that increase in volume is going to equal a decrease in pressure. And the goal, once again, is to be less than 760 millimeters of mercury. Right? You want to be less than 760 millimeters of mercury, because if the pressure is less than 760 millimeters of mercury, air is going to move into the lungs. And this process of inspiration can continue. I will say that the contraction of the diaphragm accounts for about 60 to 75% of the total increase in volume. So as the diaphragm is contracting, that is accounting for 60 to 75% of the overall increase in the volume within the thoracic cavity. The external intercostals, the scalenes, and really the sternocleidomastoid all are also players in that, but again, to a much, much smaller degree. And so, what does this all look like from the perspective of pressure changes? In other words, where do we see this change in pressure? And what you need to understand is that we have two different pressures that we are dealing with. We're dealing with a intrapulmonary pressure, and the intrapulmonary pressure is the pressure actually within the alveoli, within the lungs. Right, and so this right here is inside the lungs. Right? We're talking about the pressure within and surrounding the alveoli. All right. Intrapleural pressure is referring to the pleural cavity. This is what is surrounding the lungs, and we know that any kind of cavity, pericardial cavity, abdominal cavity, thoracic cavity, pleural cavity, cranial cavity, spinal cavity. I don't care what kind of cavity it is, retroperitoneal cavity. I don't care. We know that all cavities have a parietal lining and a visceral lining. And that between the parietal and the visceral, there is always a space where some kind of serous fluid is contained within the space. And the pleural cavity is no different. You have a parietal pleural lining, you have a visceral pleural lining, and in between those two linings you have a pleural cavity or a pleural space where we have serous fluid that is going to be circulating around the lungs. In fact, when you hear of someone that has fluid on the lungs, right, what that means is that they've taken on extra serous fluid. There's a backlog of fluid. There's a buildup of fluid that is surrounding the lungs within that pleural cavity or that pleural space. And this serous fluid is actually regulated and drained through the lymphatic system. And so there's a tie-in here with regulating that pressure and the amount of fluid that is there from within the lymphatic system. And so what we see happen here is, and at rest, the intrapleural pressure is 760 millimeters of mercury. All right. Which is equal to the atmospheric pressure. Right, and so this is in the lungs. Right, this is in the lungs. When we increase the volume of the lungs, we decrease that pressure within the intrapleural space within the lungs, and the key is to drop that down to about 758 millimeters of mercury. It doesn't have to be a huge pressure decrease in order to go ahead and force air to move into the lungs. Well, how do we aid that drop of intrapulmonary pressure? How do we aid in that drop of the decrease of the pressure within the lungs? And the answer to that is we rely on the intrapleural pressure. Right? We rely on the intrapleural pressure, not the intrapulmonary pressure. So what role does the intrapleural pressure play? Well, that pressure is what is created from the fluid that is surrounding the pleural cavity. And that pressure is always less than 760 millimeters of mercury. In fact, the intrapleural pressure is roughly about 754 to 756 millimeters of mercury. And that's a constant. Right? That's a constant. Well, this is important because what ends up happening here is, and you kind of get this imagery going, the visceral pleural is directly attached to the lungs. Right? The parietal pleural is what is attached to the thoracic cavity. And the serous fluid that is within that space between the visceral and the parietal pleural creates negative pressure because, again, the pressure within that space is less than the atmospheric pressure. And as is the case with negative pressure, this is exactly what we saw within capillary beds that drives filtration and reabsorption. We know that negative pressure acts as a suction. All right. And so what happens is the serous fluid acts as a vacuum or a suction with its negative pressure at 754 millimeters of mercury, less than that of the atmospheric pressure, it pulls, or it's suctioning, the visceral pleural, which is now pulling on the lungs. Right? That's what keeps the lungs open. Right? That's if you didn't have that, the lungs would collapse in on itself. Think about when someone is diagnosed with a collapsed lung. What that means is that intrapleural pressure is no longer less than atmospheric pressure. Right? So you've breached the pleural cavity, and you've lost that negative pressure. And so what happens is the lung collapses in on itself because there's no longer any tension holding it open. Right? And the reason why that happens is because of all of the water that is within the lungs. That water wants to adhere to itself, and so it comes together because there's no more resistance, and it collapses the lung. All right. So that pleural cavity at negative pressure is pulling on the visceral pleura, and as it's pulling on that, it's suctioning against the parietal pleura, which is attached to the thoracic cavity. Why is that important? Well, continue this train of thought. When the diaphragm drops and the external intercostals, with support of the scalenes and the sternocleidomastoid, when they contract and expand the rib cage, what are you expanding? The thoracic cavity, which is pulling on the parietal pleura, which is pulling on the visceral pleura, which is pulling on the lungs and expanding those lungs even more. And when you expand those lungs even more, you drop that pressure below 760 millimeters of mercury. Take this back to Denver with us. We talked about Denver in the last video. Right? Take this back to Denver. Denver, we said that it was, 628 millimeters of mercury. If my old brain is remembering, I'm double checking my notes to make sure that I didn't screw that up. 623. I was off by a little bit. 623 millimeters of mercury. If you're in Denver, because you're a mile up into the atmosphere, you're a mile away from sea level. So what does that mean? The rib cage the diaphragm has to contract even more. The external intercostals have to contract even more. You have to expand that rib cage to a greater degree. Why? To pull on the parietal pleura, which pulls on the visceral pleura, which expands the lungs even more to do what? Now you've got to drop that pressure not below 760, you've got to drop that pressure below 623 millimeters of mercury. All right, so this all functionally does tie in and relate to what we've been talking about. Again, at sea level, for us at normal altitude, if you want to consider that to be sea level, the goal is to decrease that pressure below 760. That happens relatively easily, all right, without much force. Think about just sitting here and just engaging in what we call tidal breathing, all right, or that tidal volume, right, TV. It's about 500 milliliters. It's a half a liter. That's how much air you are breathing in, inspiring, and expiring on a normal cycle. And that doesn't take much work to do. That doesn't take much work to do. You can do that pretty much just by contracting the diaphragm down. You can create that pressure difference to go ahead and drive that into the lungs. And so this is what this all looks like. Just from a graphical perspective, again, at rest, the intrapulmonary or the intra-alveolar pressure within the lungs, the alveoli, it's equal to atmospheric pressure. There is no movement of air. Right? So the diaphragm is relaxed, the external intercostals are relaxed, everything's relaxed. There's still tension on the lungs, because remember, otherwise the water that's within the lungs would cause it to collapse in on itself. All right, and so there's still pressure there, but it's equal to that of the atmospheric pressure. Once the diaphragm contracts, once the external intercostals contract, it pulls on the parietal pleura, which pulls on the visceral pleura, which pulls on the lungs, which increases the volume, which drops the pressure. And again, we're talking about a very small drop in pressure to force air to move into the lungs. All right? And in order to engage in expiration, you would do just the opposite. You would decrease the volume, which would increase the pressure intrapulmonarily, right? or within the lungs. And again, you're not increasing that pressure by much. Just as long as it's above 760 millimeters of mercury, you are perfectly fine. You are acceptable. Right? So 761 millimeters of mercury is enough to force expiration to occur, because the alveolar pressure is now higher than the atmospheric pressure. All right. So what regulates our pattern of breathing? Well, this is another good question. And what we need to understand is that there's actually coordination within the brainstem that regulates the rhythm and the force of the breathing. Right? And your primary areas within the brainstem that is regulating breathing is your medulla oblongata, which we know is actively engaged in the regulating of cardiac rhythm, and the pons. All right. In fact, there's 3 respiratory neural groups that are regulating rhythm and force of breathing. Right? The ventral respiratory group and the dorsal respiratory group are both located within the medulla oblongata, or close proximity. And it's the pontine respiratory group that is located within the pons. All right. And so remember that the medulla oblongata kind of sits inferiorly to the pons, and so that is all right there. And so what does this all look like? How do these 3 areas come together to coordinate this breathing pattern? All right, and because you're not always just doing tidal breathing. All right, sometimes you are more shallow than that. Right? Sometimes you need to get up and go. Right? And therefore you need to increase that. And so how does that all happen? And so let's go ahead and let's talk about this and see what we can make of this for today. So the first area that we need to look at is the ventral respiratory group, because this is your primary area of regulation. Right? It is your ventral respiratory group that is coordinating basic tidal breathing. Right? So just moving those 500 mils of air in and out is being regulated right here through the ventral respiratory group. And much like in the cardio system, we learned that there was the sinoatrial node within the heart. The lungs are regulated through an SA node of their own that's called the pre-Botzinger complex. And the pre-Botzinger complex is what is responsible for the generation of the rhythm for breathing. Right? And it does that. The pre-Botzinger complex regulates that rhythm of breathing through coordination with the dorsal respiratory group, the DRG, right? And so it works with the dorsal respiratory group to go ahead and really manage the generation of the rhythm of breathing. All right. Um, and it's doing that through regulation, or I should say stimulation, um, or inhibition of inspiratory neurons and expiratory neurons. And so the pre-Botzinger complex is what is going to stimulate neurons that are going to lead to inspiration, and then it will inhibit those neurons and activate expiratory neurons. And so as expiratory neurons begin to fire, the inspiratory are inhibited. When inspiratory neurons begin to fire, the expiratory neurons are inhibited. And typically each one of these cycles takes about three to 5 seconds. All right. Usually you can get 12 breaths in a minute. All right. Usually you can get about 12 breaths in a minute. So inspiratory is looked upon as taking about 2 seconds. Expiratory is about 3 seconds. So that's where I'm coming up with that 3 to 5 seconds, all right, per breath cycle. And you can do about 12 of those in a minute, right, if everything is working the way that it should. So this is all regulated through the pre-Botzinger complex. Now, the dorsal respiratory group, all right, is going to modify the ventral respiratory group. So the dorsal respiratory group regulates the ventral respiratory group, the VRG. Right? It's regulating the VRG. We know that is where the pre-Botzinger complex is. So that's kind of where the rhythm generator is coming from. And so it helps the VRG adapt to rhythm and speed. Right? It does that through chemoreceptors within the medulla. It does that within chemoreceptors that are found within the medulla, and those chemoreceptors are playing off of chemoreceptors within the arteries, and or stretch receptors that are within the bronchial system. And so what kind of chemoreceptors are we looking at? Well, specifically what we are looking here is we're looking for coordination between the medulla and the arteries that are monitoring CO2 levels. Right? This is specifically the physiology that we're monitoring. If CO2 levels increase, all right, if it increases, that means that you have a high pH. All right. And so if you have a high pH, within the blood, then what's going to happen is you're going to increase the rate of respiration. All right? And so that cycle of every 5 seconds doing a inspiration and expiratory cycle is going to be shortened. Why? Because that's going to force carbon dioxide to be removed from the body more quickly. Right? It's going to force it to be removed from the body more quickly. All right. Just like any kind of irritant within the bronchioles is going to trigger the dorsal respiratory group, because keep in mind things like coughing, right, things like sneezing are all regulated through this process as well. They're all modifications of breathing pattern. And so this is all going to be regulated through the DRG. The PRG, the pontine respiratory group, or the pneumotaxic respiratory group, is within the pons, and it also modifies the ventral respiratory group. This time, it's regulating that through coordination with pretty much the cerebrum. Right? So the limbic system, which is the emotions, the hypothalamus, which is just about everything from hunger to thirst, to autonomic response, to sex drive, to sleep patterns, all of that. All right, combined with the limbic system, which is emotion, and the cerebral cortex, especially the frontal part of that, where you get a lot of your personality from. The pontine is now going to regulate the VRG based off of those sensory inputs. And so the way that it does that is through altering the duration of, or the intensity of, the breath. All right, so when you're sleeping, your breaths are going to be a little bit shorter and they're going to be more shallow. When you're exercising, those breaths are going to be deeper and they're going to be longer. Right? When you are vocalizing, you're going to have possibly a shorter breath that might be more shallow, could be a little bit longer. That can really vary. Crying, you're going to have short breaths that are much deeper. All right. So think about that. So you're exhaling, and all right. So you're sucking in all that air, and then and so you're kind of getting air in, and then quickly getting it out in between the spats of crying. What some of you probably do before and after exams in anatomy and physiology. And so the dorsal respiratory group is modifying the VRG based off of systemic changes throughout the body. The PRG, the pontine respiratory group, is modifying breathing patterns based off of sensory input from directly the central nervous system, right? Specifically the cerebrum. Right? And this is what all of that kind of looks like put together. Right? So you can kind of see where everything is located. Right? Again, here is the pons. Here's the medulla oblongata. Right? You can see right here, this is the DRG. And this is the VRG, where the pre-Botzinger complex is located. And then the PRG, the pontine respiratory group, is again up here in the pons. And so all of that is being now coordinated and managed. And this here is just a nice little summary table of exactly how the DRG is going to be, again, regulating the VRG. All right, and again, this here is a nice little flow chart as well, where the DRG can stimulate the VRG. All right, as far as how it's going to alter that during altered breathing patterns as opposed to normal quiet breathing patterns. And this is just the negative feedback system. All right, so arterial partial pressure of carbon dioxide is going to decrease. All right, I'm sorry, it's going to increase. All right, which is going to decrease the pH, all right, or it's going to cause a decrease in the partial pressure of oxygen. All right, and so chemoreceptors are going to determine that. All right, that's going to stimulate the dorsal respiratory group in the medulla oblongata to go ahead and stimulate the ventral respiratory group, which is going to cause the external intercostals to contract more, to expand the rib cage more. It's going to cause the diaphragm to contract more to bring in more air, and it's also going to cause a more forceful, on the flip side of that, it's going to cause a more forceful exhalation. as well, again, to push that carbon dioxide out more and to bring more oxygen in. And so by doing that, by causing a deeper, more forceful inhalation and expiration, that's going to decrease the partial pressure of carbon dioxide. It's going to increase partial pressure of oxygen, and it's going to increase the pH. In other words, it's going to make it less acidic and more baseline. All right, remember, the pH of blood stays between 7.35 and 7.45. All right, and once you've decreased carbon dioxide levels, once you've increased pH, once you've increased partial pressure of oxygen, then this negative feedback system is once again in homeostatic balance. And so that's kind of how we regulate breathing. Right? That is how we regulate these patterns of breathing. And so with that, I'm going to leave you to ponder what it is that you have just learned and gone through. Keep jotting down those notes, keep asking those questions, and I'll catch you later.